Hi, everybody. Welcome to Soft Earth 6. The topic is landscapes are memories, okay? And that, like other topical titles, is meant to be a little bit enigmatic, and the enigma will be revealed as we go along, right? So I'm starting with a demo this time, a simple but powerful demo, all right? This is a piece of paper. You'll note there's no distinguishing creases or lines really in this piece of paper, right? Everybody agree here? Yeah, okay. Now we're gonna take this piece of paper, right? And we're gonna violently crumple it up, right? So we're gonna apply as close to a isotropic stress as we can, which we can't really do all at once. So I just squeeze it this way, then I'll squeeze it that way, and I'll squeeze it that way. Okay, so first of all, what I want you to understand is that when I uncrumple this paper, of course, we know that it's now crisscrossed with a lot of creases that are on it, right? They're probably hard to see all the way back there and on the camera, so I'll do my little drawing on the board, right? So we had this piece of paper. We applied, as best we could, a stress in all directions. And we know that when we uncrumple the paper now, right, that what we're left with is a series of creases that look something like a network of cracks, but are not exactly the same, right? The other thing you might notice if you place this on a table is that it sort of looks like a mountain range, right? Don't roll your eyes at me. The reason I bring this up is that if you think about this situation as a mountain range, right, you can imagine a process that brings the rock or the paper together, right, causes it to buckle and fold under that stress. And what I want you to understand is that try as we might to reverse the stress condition on the paper, there is an irreversible imprint of the stress on it, right? So these cracks right here are a memory of a past stress state, right? That stress state is no longer active on the paper, and yet the signature of that stress state is there, right? And when that material that buckles or folds is actually something like rock, right? Then the memory of that stress state is also a landscape. So when I say landscapes are memories, what I mean is that literally a landscape is an encoded memory of a past stress state. That stress state might have been yesterday, or it might have been 400 million years ago, or it might be something in between, right? The fascinating thing about that memory is, like our memories, it affects what happens in the future, right? When you crumple this paper, you've changed its mechanical properties because you've created a bunch of hinges in it now. And so when I crumple this paper again, the first thing that it's going to do is deform easily and in a localized way along these hinges that I've placed in it, right? And so the memory that is encoded from the previous stress state is encoded in the buckling or breaking of bonds along these creases, and that has changed its mechanical state forever, right? So we can think of maybe a more direct landscape example, right? So we're going to travel to the beach. It's early November now. Public service announcement to you all. It's still great beach weather down at the New Jersey shore, okay? The water temp is still pretty warm. You can even go swimming if you want. All right, so you're at the beach, okay? Here we are, standing close to the water's edge. The water's edge is here. And you approach the water's edge, and what you see is a little series of sand ripples, okay? These sand ripples, if we estimate their wavelength, there's something like, 10 centimeters, 10 to the minus 1 meters in wavelength, okay? Their amplitude is only a few centimeters high, right? These are just cute little sand ripples that you see at the edge of the beach. Now, These sand ripples, if they are pointy and they are symmetric, meaning they're not skewed to one side or the other, we know just by looking at them that they were formed by waves, right? They're formed by the back and forth motion that comes when a wave comes and breaks onto the sand and then washes away, all right? So we know that these sand ripples were formed by waves, but we come upon the water's edge and we realize that the water's edge is no longer inundating these sand ripples, okay? So these sand ripples were formed under the water, and now they're sitting there exposed above the water. Now, you don't need to know very much about sand ripples to understand that these ripples were formed by water waves. The water waves are no longer there, and you would deduce, because there's really no other option, that the tide is dropping, right? So you would deduce that at some previous time, the water level was up here, the sloshing motion back and forth was creating these ripples, and now the tide has gone out. It has left these ripples high and dry, right? And so we are looking at a landscape. It's a landscape of tiny ripples that was formed under one stress condition. That stress condition is no longer there because the tide has dropped, right? And it's left them behind, okay? So in this particular case, these are tiny features. And by the way, I don't expect you to have an intuition for this just yet, but those sand ripples form on the time scale of minutes, all right? So it doesn't take very long in order to make sand ripples like that. And so these are a memory of a past stress state that's no longer there. But what I want you to understand also is that easy come, easy go. A gust of wind kicks up from a different direction, blows against these ripples. The tide comes back in, comes all the way up to here. The ripples that formed in minutes under that stress state can get obliterated when a stress returns, right? And so these are memories of a past stress state. They're easy to form and they're easy to eliminate, okay? Now let's go to our mountain range example, right? So at a much larger scale, we'll imagine a mountain chain. So this is like our crumpled up paper, right? So it's got some river valleys coming off here, if you can envision it, right? We're trying to look at some perspective here, which is always a little dangerous for me, right? You can see it, right? Looking at mountains from an angle. But the point now is, think of these mountains as, here we are in Pennsylvania. So we'll consider the Appalachian Mountains, closest mountains to us. So these mountains were formed, I should ask, anybody know how old the Appalachians are, roughly, order of magnitude? What kind of geologists are you? 400 million years old, okay? These are old-ass mountains, right? Respect, they're the oldest mountains in the world, okay? So we're looking at mountains that were formed something like 400 million years ago, mega annum, right? That's the MA, million years ago. We look at the wavelength of these features. Something like 10 to the 5 meters, okay? So these are large features. They were created in geologic timescale. They were created over a relatively short amount of time. Remember how mountains like this get created. They were created by the collision of two tectonic plates, one of which subducted and one of which rode up, right? And created a mountain range. All that action went down about 400 million years ago. Ever since then, these mountains have just been getting eroded away, okay? They're still there, okay? There was a stress condition caused by a situation where these mountains were at the edge of a continent colliding with another continent 400 million years ago, right? Those mountains are still there. And if you think about what that means, right? So there's a memory of this tectonic collision. It is still encoded in these mountains. Now, these mountains used to be Himalayan sized, and they're now just about 1/10 of their former glory. Nonetheless, they still dictate the courses of water running through these landscapes. They still dictate the courses of glaciers when ice ages come upon us that move across this landscape. They still dictate where our roads go in this landscape, right? And so this memory of this tectonic collision 400 million years ago has a legacy that impacts all of the physical and human development aspects of this landscape 400 million years later, right? Which I find pretty remarkable, okay? That is a long memory, right? And so you get the idea then, right, that like small landscape features form over short timescales and they get erased over short timescales. Big landscape features take longer to make and it can take a lot longer to get rid of, right? So you could imagine making some kind of plot that is a logarithmic plot. Of course, I always draw it on log scale. This axis is time, and it could be something like time of formation and also of erasure, right? And this would be something like log of length, wavelength, or size, okay? So you have our little sand ripples down here, okay? This might be something like minutes. Sorry. This might be something like, 10 to the minus 1 meters. You have something longer. You have sand dunes in here, right? I'm always, for some reason, bad at drawing those, right? But here's my little Barkan sand dune. We're now looking at it from above. These things form on the time scale of decades. They've got wavelengths maybe of something more like 10 to the 2 meters, right? And then all the way up here, we have our mountains, okay? And there's not any kind of universal scaling for something like this, right? But you could roughly imagine, right, that there's some kind of power law increase in the amount of time that it takes to form and erase features depending on their size, right? One way to think about that then, right, is that, with the tectonics, we are living in the legacy of landscapes that were formed a very long time ago, and they continue to affect the material and energy fluxes through these environments, right? When we think about even smaller timescales, right? So we think about here in Philadelphia, the Delaware, the Schuylkill River, they are not as old as the Appalachian Mountains, but they've been around for a few 100,000 to millions of years, right? And they're evolving very slowly. At some point, they will no longer be here, right? But right on our timescales, they are permanent features of the landscape. We dive underneath the water in these rivers, and we would see sand dunes on the bottom. In some cases, they can be large. They tend not to get as large as they do in the desert, right? But those sand dunes will evolve in a river over years, but we wouldn't expect that the same sand dunes at the end of our lifespans are the ones that we had at the beginning of our lifespans. And then we have something like, these little tiny wave ripples or windblown ripples on the beach that we all understand are very ephemeral, right? And so the reason I bring this up, one reason is that when we go out to the landscape and we want to think about physics, right? We want to think about generalized principles. We want to think about F equals ma kind of stuff that we can do, right? So we want to think, oh, I'm interested in mountains. So I probably, as we've learned, and we'll talk a little bit more, there's a buckling instability that happens there that generates this wavelength. And sand dunes, I can think of a fluid mechanical instability that generates them, right? And ripples and meandering rivers and so on. And indeed, that is all true, right? Everything follows the rules of physics, and there are physical principles that we can all use to understand those landscapes. But the other thing that we need to think about is that the stresses that act on the landscapes right now are not necessarily the stresses that made them, and that the landscapes that are created by stresses in the past create or modulate stresses that Earth materials feel now. If you think about the steepness of a mountain range and the soil that's on it, right? So the mountain evolves over millions of years. The soil that forms on it forms over 1,000-year timescales. What you need to understand is that from the perspective of the soil, The mountain is just an imposed boundary condition, right? What I mean then is that, right, the past stresses that form this landscape modulate the stresses that move through that landscape and act on Earth materials now. Okay? Does that make sense? So, how do you erase these features, right? We talked about formation. How do you erase them? So, for the granular ones, right, whether small sand ripples or big sand dunes, they are granular landforms. For these granular ones, the way that you do it is you fluidize or suspend, right? So we talked about this before with sand dunes, that if the wind blows too hard or if there's sand dunes underwater, if the river current moves too strong and grains of sand get picked up so that they can no longer get trapped in the downwind side, if you suspend sediment, basically what you do is you obliterate these things, right? So suspending or fluidizing this material is basically going to erase these memories. If you think about the mountain range, well, you have to erode it, which is very slow, and or you eventually have to subduct it, right? This process. Take the crust material and jam it underneath of another one, and it'll eventually melt away when it gets deep enough, right? So, this is an idea about, memory creation from the perspective of the landforms. So now I want to talk about memory creation in terms of patterns that we see inside of these granular landscapes, okay? So we're going to now focus on these. And what I'm going to talk about is that you can take these kind of landforms and you can dissect them. You can cut them open and look at them. And you can see features embedded in them that tell you a little bit more about their history of formation, okay? So we'll start with a sand dune, okay? And I'll make it yellow to keep with the theme of yellow sand. So here's our sand dune. The wind is blowing from left to right. And so we'll draw this cross section, right? This is looking down from above, and now we're going to look at a topographic cross section. Okay? So this is what the sand dune looks like. Okay? As we know, we talked about last time, the flow speeds up across the dune. That causes sand grains to hop across the dune and then get trapped in the other side. Over time, what this does is it creates, let me make sure I get my colors right. It creates erosion on the upstream side, and it creates deposition on the downstream side, right? So that if this is the profile of the dune at one time, we can draw the profile of the dune at some future time, right? And what we will see is that there's a region that is eroded, the upwind region, and there's a region that's been deposited, okay? So one thing about this depositional region, this is a little bit of a subtlety, but it's going to come back in terms of understanding the deposit. The way that this is built is that sand grains actually pile up right here at the top of the downwind face. They pile up there until they avalanche. And when they avalanche, they slide down and they create these little tabular deposits. And so when the sand deposits on the lee side, it doesn't just deposit as a featureless mass of grains. It actually is a series of individual avalanches that make these deposits. So the signature of this process of erosion and deposition and migration of the dune is actually these avalanche deposits that are preserved here, okay? Now, if they're preserved here, right, so this is time 2, eventually the sand dune comes along and mows them over, okay? If the sand dune advances by depositing these avalanche deposits, then that means that the entire sand dune itself should be filled with avalanche deposits. And it is. You can think of the sand dune, it's almost like a tank tread over and over, right? So these sand grains come to the top, they avalanche down, they make a deposit. The grains that are down here at the bottom, the dune mows over them and they reemerge at the back and they go around and around again, okay? So there's a pattern that is encoded in here, and this pattern is a pattern that is larger than something of individual grains. This is not a grain scale structure pattern. This is an avalanche scale structure pattern. Give you an idea for a typical dune that's a few meters high in like a windblown sand dune. These deposits will be a few centimeters thick, and they'll be meters in spatial extent, and there'll just be many of them over and over and over again, right? This is one of the ways that we know when we're looking at a sedimentary deposit that it was a dune, because we see these repeated avalanche deposits, right? And so if you were to stand in one location and watch the dune move by, it's an asymmetric wave, basically, right? So you're here at time 0, and you're standing in one place, and then the dune's coming at you, right? And what you would see in terms of elevation as a function of time is that the elevation would rise very quickly, coming up the steep face of the dune, until you reach the peak elevation, which is the crest of the dune. And then you would see, right, that the elevation will more gradually recede. So what you see in time is a leading edge of deposition, right? But once the elevation drops below a previously obtained elevation, that's material that's getting eroded, right? So you would see this brief period of deposition followed by a gradual period of erosion. And if the back end of the dune is the same elevation as the front end of the dune, in the end, it's a wash, right? There was a period of time where sediment was being deposited and memories were being made because you were depositing sediment encoded with these avalanche deposits. And then there was a period of time where those grains just got stripped out of those deposits and shuffled around again, and the memory of that deposit was lost, right? So by the time that the dune has migrated one wavelength, what you're left with is like as if nothing happened. Memory got created in deposits, memory got destroyed by erosion, okay? So, of course, trains of natural sand dunes don't come alone. They don't fly solo. There are trains of them, and they're pretty irregular, right? So the scenario, instead of looking like this, would maybe look more like right, something like this, right? Big dunes with smaller dunes or ripples that are on the back of them, still migrating left to right, right? And in this scenario, though, same situation applies, right? You have erosion happening on all of the upwind faces, right? And you have depositional zones that are in all of these areas. But you now understand that if you were to make a time series of elevation going up and down, it would be a lot more complicated, right? Just to make a literal cartoon, it would look something like a random walk, right? I didn't draw this to correspond to that drawing anymore at all, right? Don't try to relate this to this passing by, right? But you get the idea that if we have a more random, irregular set of topography migrating like these bed forms, then you're going to get a time series of elevation going up and down that's going to be pretty erratic and kind of in the family of a random walk, okay? So this situation would make some complex stratigraphy. Stratigraphy is sedimentary deposits that get preserved, okay? So I'll write that out. That's what we're talking about. Stratigraphy is studying the sedimentary patterns that are preserved in the rocks, right? This would make a complicated stratigraphy, but understand that in the absence of any imbalance between erosion and deposition, that even if this made some complex stratigraphy temporarily, that nothing would get stored permanently, right? Land goes up, land goes down, sediment gets deposited, sediment gets eroded. Whether that's simple or whether it's complicated, if there isn't any net accumulation of sediment, there's not any permanent creation of memory, right? So in these situations that I've drawn for you, there's situations where erosion on average is balancing deposition, and in that situation you don't preserve memory. You're just constantly creating and destroying memory, so you don't have any permanent preservation. So what do you need to do? What we need to do is we need to create an imbalance. And in particular, we need an imbalance so that deposition on average is greater than erosion. This is what we need to do in order to permanently preserve sedimentary deposits, to create some memory that that landscape was there, if we hope to come back later and find that memory encoded in the deposits and say something, right? This is not a hypothetical, by the way, right? The situation of net deposition is the reason why we have rocks made of river deposits and dune deposits from hundreds of millions and even billions of years ago that we can read today, right? We can walk up to an outcrop and we can know that there was a river in the middle of a giant desert today because we see the sedimentary deposits of it, right? So we need something to create this imbalance so the deposition is greater than erosion, right? So I'll just give you one example. One example is a river delta, okay? So what is a river delta? Let's imagine a river that comes down and it hits the ocean, okay? So I'm drawing a river in profile here. Don't make me draw it in perspective. It'll get gnarly, right? But so the river's here, the water's flowing down from left to right, and it hits the ocean, and we know that when the water hits the ocean, the water level's flat, the flow comes out of its channel, it starts depositing all that sediment, right? So if sea level rises, right, now we have a situation where an area before that was exposed above the water and where the river flow was moving down by gravity is now under the ocean, right? And so now, instead of sediment deposition just happening here, when sea level rises, now we have sediment deposition happening here as well, right? And if sea level rises again and floods more of the delta landscape, we're now going to have even more deposition. So sea level rise is one common situation that essentially creates permanent space for sediment to fill, right? And that will then create a situation of net deposition, right? Of course, you could also do it by land subsidence. It doesn't really matter if the sea level's going up or if the land next to the sea is sinking, right? They're both locally, it's just a reference frame switch, right? They're both going to have the same thing, which is that parts of the delta are going to get flooded, and those parts of the delta that get flooded are going to get deposition, right? So in this situation now, if we repeat our plot of elevation against time, so you still have something you will still have something that looks like a random walk, okay? I need you to understand that there's a river here, and the river is doing all its rivery things, right? It's got a bunch of sand dunes migrating along, there's turbulent flow, it's eroding locally and depositing locally, there's a lot of mess happening, right? So most of what's going on is the surface going up and down in a random walk motion. But there's this slow sea level rise that's superimposed on it, right? And so you could the sea level rise has the effect of adding a drift to the random walk, right? So there's a lot of randomness because rivers meander and migrate and got ripples and dunes and all kinds of stuff. So there's a lot of up and down, but the sea level produces this net effect of drift, right? And so what does this mean in terms of stratigraphy? So stratigraphy is essentially memories that are never forgotten, right? It is sediment that is laid down and it is never re-eroded again, right? Which means that stratigraphy is essentially a record-breaking process, right? If I make a record that I get down, if I erode down to some low elevation and then I never erode down to there again, that leaves a mark. That mark is left in the stratigraphic record. It makes these little lines. So if you want to ask what is stratigraphy, you basically you walk through here and you sequentially look at minima that are never again exceeded. And that's going to tell you about the sediments that are going to be preserved, okay? So there's one, there's another one, here's another one, here's another one. So the way to read this then is that I would have a little packet of sediment here preserved. And maybe it has some ripples and dunes in it, right? So what does that look like? You know, maybe there's some deposits like that. I have another little chunk of sediment above it that is deposited. Maybe locally the ripples and dunes are moving the other way. Who knows? And then above that, I have another little chunk preserved. So you have these discrete chunks of sediment that was laid down continuously and preserved, separated by vast expanses of time that are missing. Okay, so the sedimentary record is a very strange record because it has highly resolved little bitty chunks of continuous memory separated by unknown gaps where there's no memory at all. And I guess maybe even in that regard, it's not unlike our own memories, right? Like you have these random memories from childhood that are burned in there, separated by vast gaps, sometimes of years, where you can't recall a single thing that happened. You know, at least if you're me, right? I'm straight edge, by the way, so that's not a veiled drug reference. Got it? You're welcome. Yeah. And so these sediments are preserved because they never got re-eroded. So if you want to eliminate them, you have to re-erode them. And if there's like net drift, you're going to have more and more permanently preserved sediment. And if you want to get rid of that, you need to do something dramatic. You can either have some really big random excursion like black swan event or something, right, that cuts down, or you could just have something that happens on Earth all the time on these deltas, which is that sea level rises for 10,000 years coming out of an ice age, and then sea level drops for 10,000 years going into another ice age, in which case the river will cut down through a bunch of deposits, okay? So, I think that we all understand. Let's step back from this abstract drawing. Let's think about a very visceral example. Let's say that we took a bucket of sand today and we walked outside of this hall and we dumped it on the ground. I think we would all expect that, so here's our sand pile, right? Sorry, it looks a little bit like a pile of poo, but it's sand, okay? Here's our sand pile. I think we would all expect that if we came outside 10 minutes later, it would look pretty much like it does now, right? And let's just count that. How do we quantify it looks pretty much like it does now? Let's just measure it by either the number of sand grains or just the total volume of sand that's in the deposit, right? So we'll make a plot that is log time against the log of what I'll call fraction preserved. What does that mean? It means if all the volume that I put in the sand pile is still there, then I have fraction 1 preserved, right? I think we know that if we came back the next day, there'd probably be a few grains missing. Maybe they just got washed off by a raindrop. Maybe the wind blew. Maybe some student walked by and took some of them, right? But we would expect that most of what we put there is still there the next day, right? So there's some reduction. And you get the idea, right? That if we returned in a week, in a month, in a year, because of all the random wind blowing and rain falling and churning and all this kind of stuff, that we would expect that the preservation of the sand pile is going to go down in time, right? It's going to go down. This is like entropy, right? We're just basically there's a churn going on. We've tried to organize mass in one place, and it's just going to get distributed and eroded and transported away, right? It turns out that generically, the fraction of any deposit on planet Earth that gets preserved from the moment that you create it, the fraction of it that gets preserved decays like a power law function of time, right? It turns out that that decay is intimately related to the statistics of the up and down motion of the Earth's surface itself, right? So in a purely random walk with drift, you can calculate precisely what the power law scale will be in here, right? What if it's not a purely random walk, right? So you can have a correlated random walk. If I'm depositing sediment and elevation is rising now, maybe I am more likely to keep depositing sediment. You could imagine a situation of an anti-correlated random walk. If I'm depositing sediment and rising in elevation right now, I'm less likely to be depositing sediment and rising at some point in the future, right? So I'm taking all of the physics of this multi-body, multi-scale, turbulent flow, eroding and depositing sediment in 3 dimensions, and saying that if you want to, you can reduce it to thinking about a point on the landscape. And if you do, what you can then describe it as is a random walk, right? So every point on the surface of planet Earth we can think of as a random walk that goes up and down, subject to the whims of sediment transport, right? But the way that we take the deterministic but spatially and temporally extended, complex, hard sediment transport thing is that it gets encoded in the stochastic process language into how correlated or anti-correlated the random walk is. And it turns out that some landscapes on planet Earth are strongly anti-correlated. You imagine that if I'm depositing sediment in one place on a river delta, I build a ridge. And now I'm less likely to keep depositing sediment there, right? And I go somewhere else. But generically, when we think about preservation now of stratigraphy, it's like the preservation of our sand pile. That in general, whatever the random walk is, the preservation of sediment after it's deposited typically diminishes as a power law function of time, but the slope of that power law is determined by the nature of the up and down motion, right? The statistics of this random walk, okay? As Pete Sadler said in reference to the sedimentary record, memory is fragmentary and diminishes with age. How true, right? If you have some experience like I do, you understand that memory is indeed fragmentary and it also diminishes with age. If you think about this from the perspective of the sedimentary record, it is harder and harder to know things about the past, the more and more distant into the past we're looking, right? I think we all know that at some degree, but it turns out that it is intimately related. In fact, it is driven by the processes of erosion and deposition and tectonics, right? Every once in a while, we get lucky and we find a little piece of shrapnel from 3.5 billion years ago. By shrapnel, I mean rock, but like some little piece left behind, right? But in general, we have lots of sediments that we can find that were deposited in the last 100 or 1,000 years. It's pretty easy to find sediments deposited 1 million years ago. Very rare to find sediments deposited 1 billion years ago, and essentially almost impossible beyond that time scale, okay? So we have memory in the form of landscape topography itself. We now have memory in the form of coherent packages of sediment that we call stratigraphy. The last piece of memory that I want to talk about today is zooming in even further. It's memory at the scale of grains, right? The actual grains of sand or soil or particles that are the things that are actually moving coherently and collectively to create and drive these landforms, right? So, to give us an idea of that, we're going to return to our favorite soil-mantled hill slope, okay? And so here we are. We imagine that there's some hill slope like this. So it's got rock, fractured bedrock here. There's a layer of soil on top, right? That soil is being driven downhill by gravity, right? So there's our soil. And what we know, recall, is everything flows, right? So if we wait long enough, we know that the soil is creeping, that it has some velocity profile to it, right? There's some internal deformation. And we don't know this definitely for soils, but by analogy to our experimental hill slope in the lab, right, the sand pile, what we expect in this situation, right, is that when we think about this soil, what we know, or expect, I should say, based on the lab experiments, right? So let's think about the shear rate, right? The rate that it internally deforms, right? If we think that the soil started out as some loose pile of sand, like our sand pile, right? So as it's getting mechanically disturbed and it's creeping, so long as it doesn't yield and fluidize, the creep rate for a freshly prepared pile of sand or soil is high, but it diminishes through time as we iron out soft spots and weak points, right? In terms of the yield stress, that means that it's increasing through time, right? That initially loose soil is fluffy, it is ductile, but it has a low stress at which it fails, right? And that as it creeps and irons out all of its soft spots, that it gets stronger and more brittle, right? So we have this creep rate. We know that the creep rate is evolving as a function of time. We know that that must be related to some grain scale properties, but I haven't given you any indication yet about how, right? I come back to the crumpled paper, right? I mean, I'm not zoomed in on the granular scale of these fibers, but essentially what's happened is that we've broken or kinked a bunch of the fibers that are in here, right? So the grain scale phenomenon, the structure that we see, which is these creases, is related to an arrangement right? Or a structure that's imprinted at the scale of the fibers, which is broken, right? So there are, I'll say, two general categories by which we can change the structure of the grains to accomplish this macroscopic behavior, okay? And the macroscopic behavior I'm talking about is basically strain hardening, right? That as it's creeping, it's getting stronger, it's getting harder. How and why does that happen? Right? So one of the ways that it can happen is compaction, okay? And compaction, I think we know, is it's a volume change phenomenon, right? And we'll just say for simplicity, I'll put it in quotes, but it's isotropic. What do I mean by that, right? So if I have a collection of grains here, and I ask the question, so here they are at time 1, and I can put a wrapper around that and figure out how much volume these grains occupy, right? So compaction says I take the same grains and I just pull them together into a tighter arrangement, right? So that if I were to pull a wrapper around these ones, I would say same number of grains, same volume of actual sand grains, but the volume of sand grains plus pore space is smaller after compaction, right? And so, and I say that it's isotropic because essentially, right, we could take a granular material and just apply a stress on all ends and we can just reduce volume of the thing by eliminating pore space, okay? So reducing pore space increases frictional contact and it definitely makes the soil stronger. That's one thing that can happen, right? The other one is a little more subtle, okay? This is what we're going to call fabric, okay? So here's the premise. Let's say that we've got some collection of grains. These grains could be at the bottom of a river, for example. These grains could be on the hillside, of course, right? But they've been moving in one direction. So with the soil's case, gravity is just pulling them downhill. If it's a river, it's just gravity pulling the water, and then the water's been shearing the grains, right? But as these grains are tumbling past each other, they might happen to find themselves in some configuration that resists the flow or resists gravity a little bit more, right? Because in the situation of the hill slope or in a river, that there's definitely a sense of transport. The transport is not isotropic or random. The transport has a definitive direction. Then what can happen is that particles can happen to find themselves in some kind of alignment, like a chain, that is resisting the orientation of the stress, right? And if the grains happen to find themselves in that configuration, they're now stronger under that oriented stress, and they're less likely to rearrange themselves and fall out of that orientation, right? And so what you invariably find in the lab and in the field when you examine sheared granular materials is that you will find that there are locally densified chains of grains. By locally densified, I mean that you will find strong and enduring frictional contacts of grains, and this is not isotropic, right? They're aligned in a particular direction, right? The direction is like a classic shear thing. I mean, it varies a little bit, but it's roughly like 45 degrees to the imposed shear, right? And so this fabric is an additional effect that is not related to a change in volume, at least not necessarily, right? And as I mentioned, it is anisotropic. So, These chalk talks, I don't really give you any data, right? You just have to kind of trust me. But just to calibrate you a little bit, in experiments that we've done in our lab that simulate a river channel, right? So we just have a sheared granular flow. It's sheared by a viscous fluid. And we do tests where we shear it in one direction, and then we shear it again in that same direction, and then we shear it again in that same direction, and then we reverse the direction, right? We can do whatever we want. It's the lab. Roughly, if you look at the strain hardening that happens in our laboratory experiments, everything varies, depends on details and blah, 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 but roughly, it's about 50-50. In other words, we observe significant strain hardening over time of a laboratory riverbed. About half of that is related to volume change, just compaction from the initially loose state. But about half of it is not related to volume change. It's the development of a fabric. And this is for particles in the lab that are uniform spheres. You know, you might expect if you have elongated particles or some other kind of feature that developing fabric might even be more likely to happen, okay? So these grains are forming clusters to resist the direction of shear. This is happening in soil, I want to point out. This is happening in river bottoms. This is also happening on earthquake faults. We see it there too, right? So we know from colleagues of ours that have sampled the granular materials that are jammed in a fault that they have created shear-resistant anisotropic structures. You can actually see it literally in the ground-up pulverized particles that form what we call fault gouge, all right? So this is a memory, right? This one maybe is a kind of memory, but it's not anything you could deconvolve, right? I mean, you can ask about what's the volume state of a given granular material, but because compaction is isotropic, there's no sense to what happened. You can look at the grains and just say they're more compacted, they're less compacted, but you don't know how that happened. But when you look and you see fabric, when you see grains aligned in a certain orientation, you now understand that these grains were subjected to creep, and I'm going to draw an arrow above it to say it's a vector, right? So they were subjected to creep, and they were subjected to creep that had a direction to it. Now, why do I say that they were subjected to creep? Because you know what eliminates this structure? Fluidization, right? Grains are slowly moving by each other, and when they happen to find this configuration that's strong, they get locked there. This is a signature of grains that are very barely in motion, right? If you come along and you shake it violently, right? You will fluidize the soil. And when you fluidize the soil, all these enduring frictional contacts, they just get obliterated, right? So when you fluidize the soil, you reset the system. You eliminate all of this memory that was created over long time from slow creep, and then you start over again, okay? And so what I want you to understand here then is that creep encodes granular memory, and you could say whether you want to call it yielding, whether you want to call it fluidization, any situation where the applied stress exceeds the yield stress of the material, you're going to cause the granular structures to disintegrate, right? You drive it to yield, you drive it to fluidization, and you kill this structure, right? Remember, when we fluidize or yield, that fluids have no structural memory, right? Fluids are energetic enough, right, The particles are moving past each other all the time. And what you find is that in that super kinetic environment, there's no way to encode memory, right? So fluids don't encode memory, solids do. Creep is the deformation of materials below yield. Remember, so it's fluid-like in some slow oozing sense, but these materials are solid to our experience, right? And so sub-yield creeping materials are encoding memory at the granular scale, and fluidization, yielding, whatever you want to call it, destroys those memories. We know that this is true from a lot of experiments that we've done in a lot of different systems, okay? Way beyond what I can talk about here, right? So in the case of the soil on the hillside, if you create a landslide, you just take a bunch of material and you fluidize it, right? That's the situation where the memory gets destroyed, okay? So I'm going to make a very small, cheesy little table, okay? It's a small, cheesy little table that is just memory making and erasing, right? So, you know, memory making is like trips to Disneyland, you know, extra good time with your homies. Erasing might be like trauma, I don't know, you know, or just extreme boredom, right? Something like this, right? But in terms of memory making, from the first part of the talk, deposition is memory making, right? You can only read the memory of what happened in a landscape if the portions of the material that made the landscape are there. Erosion just takes material away, right? And it leaves behind a much more fragmentary trace, right? And so deposition is memory making, and erosion is memory erasing, right? If we think about it mechanically at the granular scale, creep is memory making, and yielding, fluidization, flow is all memory destroying, right? And so when we put it all together, we have a wide range of spatial scales of memory that are associated with the wide range of timescales of creation and destruction, right? So I'll draw like an axis. No, I won't make it an arrow. I'll draw an axis here, okay? And on this axis, let's just say that we're going to go from the scale of grains, which are sort of millimeter, sub-millimeter in size, right? We'll have marked on here the scale of ripples, right? We'll have marked on here the scale of dunes, and I haven't talked about this kilometer scale yet. And then somewhere all the way over here, right? So over here, we have our mountain range, right? Over here, we have that fabric, right? And in between, we have our ripples, we have our dunes. At this scale, if you want an example, I didn't talk a lot about this, right? But this is looking down above of a meandering river, right? So in a meandering river, also has zones of erosion and deposition, right? So Erosion happens on the outside bend where the flow speeds up. Deposition happens on the inside of the bend where the flow slows down. And what happens over time, if we take a cross-section of this, is that, let's say that there's a river channel with this shape, and this is the inside bend and this is the outside bend. That what happens over time, right, is that there's deposition on the inside bend, there's erosion on the outside bend, right? And so even though the flow in the meandering river here is from top to bottom, the channel migrates left to right, okay? Essentially, it's acting like a lateral version of a dune, right? It'll migrate one way and then it'll turn around and migrate back, right? And so we're creating memory at all of these scales. That memory is encoding it in a stress condition of a past state, but by encoding that stress condition, it is changing actually the property or the structure of the landscape so that future stresses have a different effect than past stresses would have, right? And so understanding that is maybe understanding part of the complexity of applying a lot of these concepts that we're interested in to actual physical landscapes, right? Universality, which we're going to talk about, and sort of generalized physics and statistical physics is a tool that we want to use. Fluid mechanics and stability theory are tools that we want to use. But we're also dealing with situations and environments with multi-scale memory that's been encoded by past stresses that are very different because everything on the Earth's surface is noisy and variable in time and in space and not constant. And so trying to disentangle that, maybe even deeper, trying to figure out which questions on the Earth's surface are answerable by physics and which ones are not, actually requires understanding and separating these kind of memory effects from the sort of, non-memory generalizable physics kind of things that we might hope to resolve from first principles or at least something approaching it. So that's all I got for today. Thanks for coming. Sophie, you had a question.
Yes. This is less of a content question and more of a discipline-based question.
Yes.
How do you feel about the use of the term accommodation space in the geosciences?
How do I feel about accommodation space or the use of it? It's fine. It's fine. Yeah. For those that don't know, when I drew the river delta, I said, sea level's going up or subsidence is happening and land is sinking down. And it's just a reference frame question, but they have the same effect, right? If you look at it from a Lagrangian perspective of the land surface, they're both the same, right? So in geoscience, a term that they use is accommodation space, and that is anything that creates space for sediment to fill, like the permanent creation of space, right? So geometrically, the creation of accommodation space is the thing that allows you to pack volumes of sediment into something where they won't be eroded again. And this term accommodation space gets used because of the fact that it doesn't really matter whether the land surface sinks or sea level or whatever local base level is rises, that they have the same effect. And so they just talk about accommodation space and rate of generation of accommodation space and all that thing. So I think accommodation space is fine. I think it's a convenient sort of process agnostic term. I think a lot of stratigraphy is bunk, but I think that accommodation space is a fine concept. Just because I made a snide comment. When I say that a lot of stratigraphy is bunk, especially if there's any geoscientists watching, I don't mean all of it. What I mean though is that it's just, are you a determinist or not? So it is very tempting to the point of just being sometimes done without question to look at sediments left in the rocks and to look at every deposit that's in there and to interpret every single one of them. So the dunes were going that way. And then in the next layer, the dunes are going that way. The river reversed direction, like the whole river at a continental scale reversed direction. You know? But if you understand this is a three-dimensional space with a meandering river that migrates side to side and there's a million-year gap between this deposit and that deposit, you're like, I just happened to catch one little local region of the river where the current locally was like that, and then a million years later it was like that, and it's not anything profound at all, right? So a lot of stratigraphy starts from the premise that we want to interpret every deposit deterministically, and so we do. An alternative view that I and others have espoused, which I hinted at with this random walk thing, is that you should start with the null hypothesis, that the Earth's surface moves up and down like a random walk. And that actually sets constraints on how much it's possible to know. And that amount of what's possible to know diminishes systematically with time into the past. And that anytime we want to take a deposit and interpret it, we should compare it to the null hypothesis. It's sort of like asking, is this thing like a 5 sigma event, or is this completely within the realm of what a random walking system would do? And so it's not that there's nothing useful left in stratigraphy, but it's to say that when you hold stratigraphy up to the null hypothesis random walk approach, you realize that a lot of interpretations we want to make are just mathematically not okay to make. They're just impossible. The level of determinism we've interpreted deposits at is actually not possible, right? So anyway.
Related question to this.
Yeah.
You mentioned at one point that stratigraphy is a permanent record.
Yeah.
So is that like...
Nothing's ever really permanent.
Yeah, that's exactly what I wanted to say, that it looks like it's permanent now, but we don't know what's happening.
Yeah. Yeah. So, yeah, I was not careful. I was sort of intentionally not careful, meaning I knew that when I said permanent that it wasn't true. But what I mean, let me say this in operationally useful terms. You know, this is not a course where we talk about geology, like real geology very much, right? But sediments eventually get turned into rocks. That only happens if they survive for a long time and if they get buried by enough other sediment above them that they get to this point of temperature and pressure that they, you know, get squeezed together, precipitates form between them, even they melt a little bit, other stuff happens and they become rock, okay? So that is not permanent. Those rocks eventually come up again and get eroded again. But the transition from being loose grains to being rock is like a phase transition, really, right? Once it gets fused into rock, it's now a whole different ballgame if you want to break it apart. And so permanent, nothing is really permanent. But what I mean by permanent is that, you know, we have sand dunes moving loose sand grains around. When we look at sedimentary rocks, we're looking at sand grains that are fused together because there was like 5 kilometers of sediment put above them. So when I say permanent, it's not permanent, but what I should say is for sediment to get deposited long enough that it can go through the millions of year cycle to turn into rock. Because when we interpret old sediments, we're actually interpreting old sediment turned into rock, right? It's not preserved as a loose pile of sand that's 1 billion years old. It's been fused together into a rock, right? And so not permanent at all, but what I mean is long enough to become stored for millions of years and turned into rock.